Hello everyone. Welcome to another exciting chapter of physics. Now, have you ever wondered how electric currents are generated? Is it just about connecting a wire to a battery, or is there something more to it? Well, today we are diving into a groundbreaking discovery that changed the way we understand electricity. Imagine this: you've got a magnet and you move it near a coil of wire. What happens? A current is generated. But here's the twist: it's not about just touching the magnet to the wire, it's about movement. This is the foundation of what we call electromagnetic induction, discovered by none other than Michael Faraday and Joseph Henry. Both Faraday and Henry independently conducted experiments where they showed how relative motion between a magnet and a coil can create an electric current. Think about how this concept is the backbone of technologies like electric motors and transformers. Faraday's work was the spark that started it all. Let's now dive into one of Faraday's experiments to better understand this idea. In the first experiment, Faraday took a coil and connected it to a galvanometer, an instrument that detects electric current. Now, here's where it gets exciting. Faraday moved a bar magnet towards the coil. And guess what? The galvanometer deflected, showing that a current was flowing through the coil. But here's the key point: the direction of the current depends on whether the magnet is moving towards the coil or away from it. When the magnet moves closer to the coil, the current flows in one direction. If the magnet moves away, the current flows in the opposite direction. To spell this out, the current is induced in the coil only when there is relative motion between the magnet and the coil. The galvanometer will show a deflection when the magnet approaches, and it will show the opposite deflection when the magnet moves away. It's as simple as that: motion equals current. As you can see in the diagram here, the relative motion between the magnet and the coil plays a crucial role in the induction process. Now, let's flip the script. In the next experiment, instead of moving the magnet, Faraday moved the coil itself. And guess what? The galvanometer showed a deflection once again, indicating an induced current. Whether it's the magnet or the coil moving, the result is the same: a current is induced in the coil whenever there's relative motion between the two. This tells us something important. It's not the magnet's presence that's key, it's the change in the magnetic field due to movement. To clarify, the current is induced in the coil when it moves through the magnetic field, and the galvanometer shows a deflection. The direction of this current will depend on whether the coil is moving towards or away from the field. Think of it like this: imagine you're waving your hand in front of a fan. If you stay still, nothing happens, but if you move your hand, the air starts flowing. It's that motion that makes a difference. In the diagram, you can see how the coil moves through the magnetic field, creating an induced current as it does. Let's explore another fascinating result from Faraday's experiments. In this one, he used a key to tap the bar magnet. With the key in place, the current in the coil remained steady. But here's the kicker: when the key was tapped, the galvanometer needle momentarily deflected, showing that a sudden change in the magnetic field produced an instantaneous current. So, if the key is pressed down and held, the current stabilizes and no longer induces further deflections. But when the key is tapped, there's a sudden change in magnetic flux, and this momentary shift generates a burst of current. To break it down, when the key is pressed, there's no change in the magnetic field, so no further current is induced. But when the key is tapped, the flux changes rapidly, which induces a momentary current in the coil. It's like when you flick a light switch, a sudden change in voltage makes things happen. This experiment highlights how transient changes in the magnetic field, like a quick tap, are what induce current in the coil. Now, let's get into an advanced example to really solidify this concept. Imagine we have a bar magnet moving towards a coil, and we want to calculate the induced electromotive force, EMF, using Faraday's law. The law tells us that the induced EMF is related to the rate of change of magnetic flux through the coil. So, how do we calculate it? First, recall that Faraday's law is given by the induced electromotive force equals the negative rate of change of magnetic flux. This can be written as the induced EMF is equal to minus the change in magnetic flux with respect to time. Now, magnetic flux, which we write as the Greek letter phi, is equal to the product of the magnetic field B, the area A of the coil, and the cosine of the angle theta between the magnetic field and the normal to the coil's surface. So we write magnetic flux equals the magnetic field times the area times the cosine of the angle between the field and the normal to the coil's surface. By applying this to the change in magnetic flux, we can calculate the induced EMF. As you can see, this equation involves both the magnetic field and the area through which it passes, showing that more flux change means more induced current. So, what have we learned today? First, that electromagnetic induction is all about relative motion between a coil and a magnetic field. It was Faraday and Henry's experiments that revealed the secret that it's the movement of the magnet or coil, not just their presence, that generates electric current. And second, we saw how Faraday's law provides the mathematical framework for understanding this process. The faster the change in magnetic flux, the greater the induced current. These principles are at the heart of many of the technologies we use every day, from electric motors to power generation systems. To sum up, electromagnetic induction isn't just a cool science experiment, it's the principle behind the generation of electric power all over the world. I hope this concept is clearer now. Stay tuned for the next chapter, where we'll explore more fascinating phenomena of physics.